important meeting. So I will talk about space weather modeling challenges and solutions, some of the solutions at least. As you know, the sun is continuously streaming out particles, so at a rate of 10 to the 9 kilograms per second. And this wind fills the entire solar system, which we call the heliosphere, where the sun has a dominant influence. And the particles actually are low energy particles, and I'm talking about energy between 0.5 and 10 kilo electron volt. There are actually two kinds of winds. It's a bimodal wind, so there's a fast and a slow wind, but this is relative, of course, because even the slow wind is at 300 kilometers per second, so this is 1,000,000 kilometers per hour, and the fast wind is at 750 and more kilometers per second. It's not only the speed that is different, it's also the density, and the chemical composition of the two winds is completely different, actually. Now, this wind directs out of the solar magnetic field, and so it creates what we call the interplanetary magnetic field, which forms a spiral structure because of the rotation of the sun, as you can see in this animation. Now, on top of this continuous stream of plasma, we have transients. For instance, solar storms, which cause coronal mass ejections. These are enormous clouds of hot plasma. These are launched into space at propagation speeds of typically 450 kilometers per second, but can be much faster, up to 3,000 kilometers per second and even more. There's also, of course, solar flares. These are intense releases of high energy radiation in short wavelengths, so high energy, so EUV, X-rays, gamma rays, and these accelerate particles due to the magnetic reconnection. There's a lot of particle acceleration. You can see the result on the CCD camera of these particles hitting the CCD camera in this small movie. Coronal mass ejections can also accelerate particles, in fact. So this is a sketch of a coronal mass ejection, how it looks like, and it creates, of course, a shock in front of the coronal mass ejection. And in this shock, you can also actually accelerate particles, and these are called gradual SEP events, which are actually the most dangerous because they can get the particles to very high energies. All particles are involved, electrons, protons, and heavier ions, and the energies range between kilo electron volt and even giga electron volt. So 1 mega electron volt proton, for instance, travels at a speed of 14,000 kilometers per second, and a giga electron volt proton travels almost at the speed of light. So these particles are much more energetic than the particles in the background of the wind. There are charged particles, yeah, so they feed the magnetic fields and they make this spiraling structure around the interplanetary magnetic field. Of course, there's some cross-field diffusion, but generally speaking, they follow the magnetic field lines. This brings us to space weather. The definition that I like the most is the one in the National Space Weather Program of the United States. So it refers to conditions on the sun and in the solar wind, but also in the magnetosphere and the ionosphere and thermosphere of the Earth that can influence the performance and the reliability of our technical systems, both spaceborne and ground-based. And it can also endanger human life and health that is related to radiation. The major drivers of the space weather are coronal mass ejections. They are not the only ones, but the major ones. Here you see a speeded up movie of the August 1999, which was during solar maximum. And so there you can see that there's a lot of CMEs actually occurring, several per week. The dangerous ones are the halo CMEs that you see all around the sun because they are coming in our direction. About 10% of all the CMEs has some influence at Earth. Yeah, so somehow. As I mentioned, there can be up to 3,000 kilometers per second. The mass is also gigantic. The largest CMEs have 10 to the 16th grams of plasma, which is comparable to the Himalaya, the mass of the Himalaya, and the energies are also gigantic. At 10 to the 33 ergs, it is really order of 5,000 atom bombs or something. So it's really huge. The most violent events in the solar system. Why do I focus on coronal mass ejection? Because they are the most dangerous drivers of the space weather. They create radiation, energetic radiation in the radiation belts, the Van Allen belts, and they have a lot of effects, negative effects. So of course, radiation of astronauts. We are protected by the atmosphere and by our magnetic shield, but the higher up you go, the less protection you get. And of course, in the International Space Station, the astronauts, if they do an EVA, an extra vehicle activity, if they go outside the space, the facility, they get radiated during a storm, so they should try to avoid that. But also the instruments on satellites are, of course, often damaged. They degrade because of the space weather, but also at Earth, actually, there's a geometrically induced currents in the power system. So in the long, anything that is long and conducting can, of course, get these currents, like also oil pipelines. They corrode like 2 times faster because of these currents that go through them. And of course, anything that is depending on satellites, like GPS, navigation, telecommunication, and stuff. So there's a lot of negative effects, a lot of damage to these technologies. Space weather is very complicated. It's a multidisciplinary research area, because I mentioned the CMEs, but it's much more than that. There's, of course, the solar flares, there's a CME onset, there's the evolution of the CMEs, the shock waves they create, and the particle acceleration they also generate in the shocks. And then, of course, last but not least, the impact of the CME at Earth also needs to be modeled. So you need to have a good model of the magnetosphere and the lower layers in the atmosphere of the Earth to kind of quantify all the different effects. So the effects I have mentioned, and so the estimated average economic cost is $10 to the 10th per year, so $10 billion per year. This is during the normal space weather operation, like we have the everyday space weather. So the socio-economic impact is rather gigantic, but what we are most afraid of is an extreme event. So an extreme event like the one in 1859, the Carrington event, there was a huge solar flare, and that happens not too often, only every 100 or 200 years. But if it happens, if that would happen now with our current technology, all our satellites, it is estimated that one such extreme event could cause some socioeconomic damage of $2.7 trillion. So that's a really recent estimate. So there is some people maybe should get muted. There is some need for space weather prediction. So this is the challenge. What are the solutions? Well, the solutions are numerical simulation models, physics-based numerical simulation models. And I will just introduce you to some of them that we are developing here at Leuven. Well, Anwisha this morning already spoke about EUHFORIA. I guess some repetition, it does not harm. I will first introduce EUHFORIA, and then I will introduce the improvements that we try to create on EUHFORIA in 2 different projects, an Horizon 2020 project from the EU, which is called EUHFORIA 2.0, and then there's also an ESA project called Heliospheric Modeling Techniques, where we also get some funding to improve the EUHFORIA. EUHFORIA has 2 parts. There's a coronal part and a heliospheric wind and CME evolution part, and both parts are actually improved or speeded up in this project. We have developed a new coronal model, global MSG coronal model called the Coconut. I will talk about it soon. And we also have optimized the heliospheric part, which we call them ICARUS. I will come to that. And we also have advanced CME flux-rope models. And last but not least, very important is also the coupling of EUHFORIA with other models. I will come to that. So EUHFORIA, as Anwisha explained, is an acronym for European Heliospheric Forecasting Information Asset. It consists of a coronal model, which is a very simple model in EUHFORIA because time matters. We need to have if you want to do a prediction, you need to do the simulations in a relatively short time scale so that you can, the computation time should be shorter than the arrival time of the CME, which is like 2 to 3 days on average. Although the fast CME, the really dangerous ones, they can be here in as little as 1 day. So in EUHFORIA, the standard EUHFORIA, the solar wind starts at 0.1 AU, and we have a simple Wang-Shili arch coronal model to just provide the input at the boundary conditions for the wind model. This is based on Gong adapt magnetograms and potential field source.
Kerem'in gözüne arı sokmuş Bodrum'da.
Kime?
Kerem'in gözüne arı sokmuş
Could you
Bodrum'da.
please mute? Everybody should mute, please, because it's.
Kindly unmute. Kindly mute your mics. Those who.
Bir de arı sokuyor.
Please mute.
Yeah, please mute your mic.
Yeah, thank you. And so we have also different CME models. I will come to that later. And so the heliospheric part goes from 0.1 AU to 2 or 2.1 AU. Of course, we can go further. We go to 2 AU because it includes the orbit of Mars, which is at 1.6 AU, but we can also go to 5 AU, and we do that actually for particle simulations. We go to up to 5 AU to orbit of Jupiter. So this is a full MHD 3D time-dependent simulation, finite volume method with constrained transport to avoid DFB, artificial DFB generation. This is what we do. We just extrapolate the values we get at 0.1 AU to 2 AU, and then we kind of do an MHD relaxation. And this is what you see here. The sun is rotating, so you get this spiral structure for the background wind. And this after like 14 days, not in real time, this just takes a few minutes on the computer, but we do an evolution of 14 days, and then the solar wind has relaxed. We get a steady rotation of the solar wind, rotation with the sun. And then on top of that, we actually put some CMEs, and then you get this picture. We do not show the 3D result because it's kind of not clear. So we make cuts in the equatorial plane and in the meridional plane of the Earth. The blue dot here is the Earth. The other dots are the other planets, Mercury and Venus. And here we have Mars at this particular time. And then we have also, we can put, of course, the satellites, stereo A and stereo B. We also can put PSP, solar orbiter. No problem, we can predict the solar wind and the CME arrival at any position in the heliosphere. At the bottom, you see a comparison. Well, I should maybe run this movie. So you see the solar wind is rotating. Then on top of that, we get the CMEs. And for this particular period, there were like 6 CMEs. And at the bottom, you see a comparison of the data just in front of the Earth at L1 in red, and in blue is the simulated data with EUHFORIA. And you see, of course, that we have some, there are some improvements necessary. The first little shock here is smeared out because of the low resolution. We need to keep the resolution low because of the time. We have to do the simulation fast. The second shock here arrives a bit too late, a couple of hours too late in the simulation, but it's at the right strength. While the third shock arrives exactly on time, it's way too strong in the simulation. So there are reasons to improve EUHFORIA. And so it is a data-driven program. So we use not only the magnetogram for the background wind, so it's based on a real measurement of a magnetogram. It can be Janus, Gong magnetogram, also Gong adapt magnetogram, HMI, MDI, MWO. We use all kinds of magnetograms, and sometimes we get better results or worse results. The best results are actually with HMI. Then we have a coronal model. This is a very simple one currently in EUHFORIA, so the Wang-Chili arch and the Schatten current sheet model to get narrow current sheets, to get the boundary conditions at 0.1 AU, and then from there we have the physics-based MHD model. But also we use data for determining the parameters of the CMEs. So there's the coronagraph imageries like GCS and StereoCat are programs, software that we can use to determine the width of the CME or the speed of the CME. And so we have different CME models. We have the cone CME, a very simple model, which is also integrated in Enlil, but we also have spheromak, torus model, Fry3D, etc. I will show you some of these results with these different CME models. So I mentioned that we have different CME input parameters. Actually, for the very simple model, the cone CME, which was the first model that was also integrated in Enlil, this is actually just a pulse, so a sphere of high density, high pressure plasma, no magnetic field, to just create a shock wave and to predict the time of arrival of the shock created by the CME. Nothing more, nothing less. This simple CME has already 7 input parameters: speed, of course, insertion time, longitude, latitude, and the width of the CME, also the density and the temperature. For the 5 first parameters, we can use 3D reconstruction techniques with a gradiated cylindrical shell model, GCS model. For the last 2, actually, we have no input from observations. We have no measurements of the density, no measurements of the temperature. So we take in prediction mode, of course, we take default values. Of course, when we do a historic event, we can play with these parameters to get a better fit of the data. When we go to a spheromak CME with an internal magnetic field, we have 3 extra parameters actually to determine the, to characterize the internal magnetic field, the flux-rope tilt, the helicity, and the flux. And we use different models. I will come to that in a bit to more detail. First of all, the parameters like the speed and direction, these are just some white light images. Here you see 2 white light images from a coronagraph on 2 different times. And this is at 6 past 3 and this is at 54 past 3. So there's 48 minutes difference. Then with this difference and knowing the we can measure, of course, how the speed will. It goes from here, from this point to this point in just 48 minutes. So you can get the derive the speed from that. Of course, there's projection effect and things like that. There's kind of an error bar, but you can get an idea of the speed. Also, the angle of the CME you can get from these white light images. And this is how we basically do it. We have programs to kind of fit the CME on this kind of white light images and get also the direction in which it is launched and things like that. The difficult part actually is the magnetic parameters. So for instance, the chirality, so the polarity of the magnetic field, this we can just derive from UV images, like here, this one. This we see, this is a S-shaped thing, so this is a positive chirality. When we have magnetograms, you can also draw the polarity inversion line, and then the flux-rope is perpendicular to that. So this is used to kind of determine the tilt of the CME. And then the most difficult part is actually the amount of flux that is reconnected. There are models like the one from Gopalswamy to measure or to estimate the total magnetic flux in an active region, but it is not the whole magnetic flux that is released, of course. Usually it's like, we estimate it's like 50% that is released, but this is the most difficult parameter to determine. There's a huge error bar on this toroidal flux. Nevertheless, we get some interesting results. So with a spheromak CME, this is like the cone CME, but with an internal magnetic field, which is an analytical model, analytical field, so spheromak. And here you see how it is a visualization of it. We get some, we can predict actually the geo-effectiveness, the impact of the CME at Earth, because this depends actually on the sign of the magnetic field, the Z component, the component perpendicular to the equatorial plane, and when it arrives at Earth. This, of course, you cannot predict with the cone CME because there is no internal magnetic field, but with the spheromak CME, you can actually try to do that. What was I going to say? So yeah, the reason is that, of course, the magnetic field of the Earth is also a polarity. And so when they both have the same polarity, the 2 dipoles will just repel each other and there will be some interaction, but not so much. But when the opposite, the CME polarity is opposite from that from Earth, there is, of course, magnetic reconnection and a lot of particles, more particles can enter the magnetosphere and cause damage on our technology. The spheromak gives reasonable results, especially when it is a front hit. So if the Earth is here, and so the top of the CME is, the nose of the CME is hitting the Earth, it is giving a good result. But of course, the CME is not a sphere. Yeah? It is a flux rope like this, all connected to the sun. Even when it reaches the Earth, a lot of CMEs are still connected to the sun. So when it is a side hit, when the leg of the CME is hitting the Earth, then we have very bad results with the spheromak because we the spheromak has no legs. So in that sense, it is not the best model. Only for head-on hits, it is a good model. We got good results. So one of my PhD students, Camila Scolino, who is now at New Hampshire in America, she got nice results for the September 2017 CMEs with spheromak. She kind of modeled the problem here. This is the measurements. There's a lot of things here. There's the velocity, where you can see there were 2 CMEs. There are 2 shocks actually. And the most important thing here is the BZ component. So you see that in the data, the black dots here, it is going negative, minus 25 nanotesla. So yeah, this is causing the impact, the huge impact of the 2 CMEs together. That was a problem because it were 2 modest CMEs, and there was not so much impact predicted because there were small CMEs, but apparently there was a big solar storm geometric storm in the magnetosphere due to these CMEs, and we were wondering how can this happen. And so in the simulations that Camilla did, we modeled both CMEs with spheromak CMEs. They were on the 4th and the 6th of September, both with a tilt of 0 degrees, so in this same direction. And with this, she could explain actually the magnetic field. You see here that the CME, the increase of the magnetic field arrives a bit too early in the simulations, the blue line here, but it has the right order of magnitude. It's just a couple of hours too soon. And also the BZ component was actually also obtained, so it is almost the right magnitude. It is just also a couple of hours too early in the simulation. But this allowed us to kind of analyze what happened on that in that week with these two CMEs, why they were so geo-effective. And it was actually the combination of the two CMEs that was geo-effective, not the CMEs themselves. So the second one catched up with the first one just before it reached the Earth, and the plasma between the two CMEs was squeezed, and this was causing the negative BZ components. It was a kind of detailed analysis that was possible thanks to this advanced modeling. So this mystery of the geo-effectiveness of the two CMEs was solved in this way, which is actually kind of scary also, because it means that you do not need a big CME to cause a geometric storm. Also, the timing of small CMEs can actually, the interaction of the two small CMEs can actually also cause a geo-effective impact of the CMEs. So we want to do this kind of predictions also for extreme events. But due to the uncertainty of the input parameters, we need to do the simulations fast enough, because the uncertainty of the input parameters travels through the models, of course, and gives some uncertainty on the model, the parameters that we want to predict, like the time of arrival and the impact of the BZ component of the magnetic field at impact. And so this is solved with kind of uncertainty quantification, which means in fact that we need to do not only one simulation, but to capture the uncertainty of the input parameters, we need to do an ensemble run, as they say, different combinations of the input parameters. And we have three different input velocities, the minimum, the average, minimum, maximum, three different spread angles. And so we have a lot of simulations to do, because we have 10 input parameters for a spheromak. We cannot do 3 values for all of them, because we would have 3 to the 10th simulations. That will be really too much. We try to limit the ensembles, and with uncertainty quantification now, which is the mathematical technique to kind of quantify the uncertainty in the model, we try to figure out which of these 10 input parameters are affecting the quantity of interest, as we call it. So for instance, the time of arrival or the BZ component. And if you can limit it to the 2 or 3 or 4 maybe most important input parameters, we can make ensembles of 3 to the 3rd or 3 to the 4th combinations, and that would be feasible to do like 30 or 40 runs. We can do them in parallel and then still do the analyze the results before the CME actually arrives. Now, so we need to speed up things, and that's why we started these two models, these two projects that I mentioned before. I'm going to talk about 2 of the results, the coconut model and the ICARUS model. Let me start with the coconut model, which is a new global MSD coronal model. What is new about it? Well, there are, of course, existing coronal models, but in coconut, we base it on a cool fluid. This is a framework that already was pre-existing. We use a finite volume method and an unstructured mesh. So one of the problems in modeling of the corona is the singularity you have in a spherical grid at the poles. And yeah, there are different solutions to that, but the good solution is, of course, to have an unstructured grid, because then you do not have any singularity. We use ideal MHD. We don't need limiters. We have no B0 plus B1 splitting necessary. We have only polytropic heating for the time being, but in a few weeks from now, we are calibrating the different terms, the heating terms, the thermal conduction, radiation are all already programmed, and we are just figuring out the good combination of these. The most important novelty is actually the implicit solver that we use, because all of the global MHD models that we have are now explicit codes, or at most semi-implicit, which means that the time step is very limited, and they need to do hundreds of thousands, if not millions, of time steps. These go very fast, but you have needs a lot of them, and so that you need like 36 hours or more to converge. And that is too long, because a CME only takes 2 days. And so this is just a global model, and then we still need to do the CME evolution. So we needed to speed this up. And so we have this unstructured grid. Here you see kind of a validation simulation. Here you see a verification. So we compare to total eclipse images, because then we can see the corona, the structures in the corona, and we try to model this. You can see that we have the streamers here. And so this we try to quantify. This is with coconut, and this is with wind predict, which is an explicit finite volume model, very similar, so we can compare the two models. So what I said is we can do much bigger time steps. Here you see the CFL steps. We start with CFL 1, and then we go to 2 and 4 and 16, and here we went up to 800. So our time steps are 800 times larger than in the explicit model. And so here you see the convergence history. We converge very fast. Yeah. And so in this case, it was only up to 800, but we can go up to 2000 CFL steps of 2000. Of course, we have much more work to do in every time step. We have to solve systems of equations instead of just evaluating equations. So it takes more time per time step, but still with this implicit method, we can get a speed up factor of 35. Yeah, 35 times faster than before, which is potentially a game changer actually, because this means that instead of 36 hours to converge, we need only 1 hour. In a real case, based on a magnetogram. So this is very, very good, because that means that we can actually use this model in an operational environment. So because there we need speed. We are now validating this model. So here you see part of the validation. We, of course, we have the visual validation, but we also measure the orientation of the streamers. We compare to white light images of total solar eclipses to see the streamers fit with what we see actually in the corona. But we also the width of the streamers we can compare to these white light images, and we can also do topological measurements and kind of quantify how good we fit the white light images. This is a method that is proposed by Wagner et al. Procedure to kind of validate the corona model, and we are doing that now, and the paper will be published, will be submitted this week. On top of this corona model, we also can launch flux-rope CMEs. This is a modified Titov-Demoulin model that we can put on top of this coconut coronal model, and then we can let it evolve. And here you see that it is working. It's going slow, of course, because now we cannot do the implicit time stepping anymore. We need the time accuracy, so we need to have small time steps. But it is possible to do that, and we are going to try to exploit it in the near future. And then we also improved the heliospheric part, so the part from 0.1 EU to 2 EU, and that we improved by radial grid stretching and with adaptive mesh refinement, solution adaptive mesh refinement. So this is now in cool fluid, which is AMR VAC, which is also a model developed here by my colleague Ronnie Keppens. And so this is also an existing model. We implemented the heliosphere there, and here you can see a CME where we have the high resolution grid only where the CME plasma is located, and the grid is coarsening after the CME is gone again. So we have, of course, we save a lot of CPU time doing it this way. This is using a tracing function, but we can have different AMR criteria. If you want to do the shocks, for instance, in a co-rotating interaction region, we can use the divergence of the velocity as a criterion. So you put thresholds on that, and then you can only increase the grid size in the shock waves of this CIR. We can also, in fact, if we have a complete CIR, we can also say we want high resolution of the whole CIR. This is all possible. It's very flexible, and we are playing now with these different parameters to improve the modeling and to speed up the modeling, most of all. So this is not a PhD student, Tina Tim Baratashvili, who is working on that. Here you can see a result of where she refined the whole CME. This is important, for instance, if you want to quantify the deformation of the CME, of the erosion of the CME, you need, of course, to have the whole magnetic cloud in high resolution. But if you want to, for instance, derive predict the arrival of the shock, you can do only the shock. This is with a shock refine, and you combine both, of course. This is a combination of the whole CME plus the shock refinement. And with these kind of combinations, with 4 different criteria, she obtained a speed up of 28. Yeah, 28. So the heliospheric part, which is taking like 2 hours for one simulation run in EUHFORIA, can be done in just actually in 4 minutes. And this is potentially a game changer, because then we can do many simulations where we can do these ensemble runs that I mentioned, and instead of predicting a time of arrival, window of arrival time, where we say, okay, with 95% of certainty, the CME shock will arrive in this narrow window. This is potentially important. How does it work? Well, here you see the AMR of the CME as it arrives at 0.1 AU. This is a cross section of the sphere at 0.1 AU, where with high resolution of the spheromak CME. And here you can see a time series. Okay, in this particular run, the CME was arriving a bit too late, because this is the data and this is the CME predictions with different AMR levels and with and without grid stretching. But why do I show this? Well, I want to show that we can get the shock capturing is much better, of course, if you have locally a very high resolution. And this shock capturing is extremely important for the SEPs. If you want to do SEP modeling, the acceleration depends, of course, on the gradients of the velocity. And so this is why we need to capture these shocks with high resolution, because we coupled this model to our SEP, so the particle transport and acceleration model uses the wind predicted by EUHFORIA as a background. I will not talk about that today, but this is one of the reasons why we do that. So then we also have advanced CME models. I mentioned the cone CME, the spheromak CME, and then what Anrisha was talking about this morning is the Fright 3D, the flux-rope in 3D model from Alexei Isavin, which has been integrated in EUHFORIA, which is a flux-rope CME. So this is expected to yield better results when we have a side hit of the CME, like in this case that maybe Anrisha also showed this morning. So this is the Earth is here and the CME hits it. It is the leg of the CME, the side hit, and in this case, the spheromak is giving bad results. And with Fright 3D, we can improve this. Like in this simulation of Anrisha, in red you have the spheromak CME. In blue you have the Fright 3D CME simulation, and in black it is the actual measurements at L1, Lagrange point 1, and you see here that it's Fright 3D, the shock arrives a bit later. The shock capturing, you could say, is the same or slightly better with Fright 3D than with spheromak. But the important, of course, is the magnetic field, and you see here that the negative BZ component you do not find at all with spheromak. While with Fright 3D, it arrives a bit too late because the shock arrives too late, of course, and the cloud arrives too late. But we have the right magnitude. It's minus 20 nanotesla for this particular case, just a couple of hours too late in this simulation. So this is a quantification that Anrisha determined from this particular case, and she's doing now more validation also of this model. The last thing I want to mention, I still have 2 minutes, I think, is this coupling of models. So this is a new trend in space weather modeling. We couple models via the modeling center, the virtual space weather modeling center, another ESA project that we are managing here from KU Leuven. Coupling of models enables better prediction. For instance, if you replace the Wang-Shili Arch coronal model by a better model, we have tried it with multi-VP, which is another coronal model from Toulouse. We actually improved the modeling of the high-speed streams in the background wind. EUHFORIA is doing bad on that, on the high-speed streams, the traditional EUHFORIA, I mean. But if you get a better physics-based, because multi-VP is also MHD-based model, you can get a better background wind, which is of course very important also for the CME evolution. And as I mentioned, we couple also EUHFORIA to Paradise, which is an SEP model. So most SEP models use analytical Parker spiral, but of course in the simulations that I've shown, the background magnetic field is all but a Parker spiral if there's a CME, because it is perturbing the field lines, of course, quite substantially. And so in Paradise, we can actually use the simulated magnetic field, the perturbed magnetic field, to compute or to quantify the particle transport and acceleration. It is not only better, but also earlier. Yeah? So for instance, when you have a magnetosphere model like OpenGDCM or Gorgon or any other model, they use usually data at L1, so measurements at L1, but L1 is just very close to the Earth, right? It's like 1% of the distance, Sun, Earth, and so when the shock of the CME arrives there, the storm is going to happen 2 hours later. So this is not really, yeah. I'm finishing. So it's not only it's not really a prediction; it's a nowcast, and by replacing measurements by simulated data 2 days or 3 days ahead, you can do a prediction 2 or 3 days ahead, not 2 hours, but 2 days ahead. So this is also very important because it gives you the time to do some mitigation and try to avoid some cases where that can be done. So the Virtual Spatial Modeling Center, I don't have time, I'm going to give a demonstration, but it is something that is actually open to everybody. We kind of put already 20 models there, we coupled the models so you can run them interactively, and the models are not all installed in Leuven, they stay with the modelers, we couple them over the internet. Yeah, so this is just a scheme that is showing how we do that, but I'm not going to go into detail. Just try it. So it's part of the ESA Space Weather Portal, and if you look for Virtual Spatial Modeling Center, you can actually ask for credentials, you will get them immediately, and you can log in and try some of the models. It's just with a GUI, graphical user interface, very simple to run the models. You don't need to install anything, just you can run the models and get the output also. It takes a while, of course, because some of the runs, like EUHFORIA, takes 2 hours to do one run, but you will get the output and can look at it in the modeling center. This is important to couple the models because, for instance, here, this is also a result from Anmisha, that where she coupled the EUHFORIA to a DST model, so for the DST index, kind of a measurement for the geomagnetic impact of the CME, a very simple one, O'Brien and McFerrin, replacing the measurements by synthetic data, which was I just explained. And so here is, you see the normal run of this DST model from O'Brien and McFerrin when you use actually measurements. But this is just a nowcast 2 hours on beforehand. While if you use the CME, the simulated data with in blue, with the Fry3D, you get the right DST index, which is like very small, minus 200 almost. It's a bit too late because as I mentioned in the simulation, also the BC component goes down a bit too late. Yeah, but we get the right amplitude of the DST index from this forecast. So this is actually, yeah, potentially important because you can forecast now 2 or 3 days in advance rather than just 2 or 3 hours in advance. Thank you.